Welcome to the Z module, and the Z module is about the alpha particles under a nuclear decay chapter. So this module is going to discuss about the production of alpha particles and the properties of the alpha particles and how these alpha particles are determined in the lab and how they are detected in the lab and how its charge by mass ratio is calculated by the simple experiment. So to start with the alpha particles, what are the alpha particles? They are just deflected by strong electric and magnetic fields, which shows that they must be the rapidly moving charged particles. Apart from this, the energy liberated in the alpha decay is also positive. And this is the evident result that we got from the semi-empirical mass formula. The nuclear structure and the characteristics of nuclear reactions also most valuable information that we could get from the alpha decay. Apart from this, the nuclear binding energies and the nuclear structure informations are derived from the energy measurements, and the determination of half-lives gives the information on the decay mechanism. The energy spectra of the alpha particles gives information about the level schemes of parent or the daughter nuclei. So this is the simple experiment to determine the charge by mass ratio of the alpha particle. So here there are slit arrangement followed by the narrow monochromator pathway through which the alpha particles which is emerging from the slit passes through this B and it gets scattered and it reaches the point called P1 and P2 on the screen. So this apparatus is used for the magnetic deflection experiment. So what is S? S is nothing but the source of the alpha particle which is set parallel to the slit B. And there is some distance between the source and the slit which is nothing but the distance A. And the alpha particles which are just coming out from the source are limited or narrowed down by the slit and they are incident on the photographic plate called P which is at the distance B from the slit. So here we can place a chamber which is placed in the strong and uniform magnetic field with the lines of force parallel to the slit. That is in the direction of the slit in parallel we can also place a chamber which consisting of or encompassing the uniform magnetic field. So under the action of the magnetic field the alpha particle will describe an arc of a circle which is represented here in the figure B of radius r, and there is only one angle of emission for which the path is through the narrow slit to the photographic plate. If the magnetic field is reversed, then the path of the particle is also reversed. The alpha particles with the velocity v reaches the point called P1 and P2 before and after reversing the magnetic field. If Q and M be the charge and the mass of the alpha particle, which is moving in the magnetic field called B, then 2dr should be equal to B into A plus B, from which we can find the ratio between Q by MB. So to get the value of Q by M, B has to be determined. So for this, the alpha particles are allowed to pass between two vertical parallel metallic plates called A and B, which is separated by the distance P. The whole apparatus is evacuated and the potential V is applied between the plates A and B. So the particles having a parabolic path between the plates and that deflection is proportional to the 1 by V squared. If 2d prime be the distance between the 2 points on the photographic plate at which the alpha particles impinge before and after the reversal of the magnetic field, and if b prime be the distance between the plate and the parallel plates, then Q by M can easily be determined. So this is the simple formula from which we can determine Q by M. And if we substitute all the values, the value of the Q by M determined with Rutherford and the Robinson was found to be around 4.82 into 10 power 7 coulomb per kilogram, which is almost close to the charge by mass ratio of ionized helium. The radon gas, which is emitting alpha particle, is placed in the thin-walled glass tube, which is surrounded by the wider tube B, which has to be evacuated. The alpha particles passing through the thin walls into the outer bulb B. After a week, the gas is collected in B and is compressed by the mercury into the fine capillary called C. So, by applying the potential difference between X and Y, its spectrum is examined. The spectrum is identified as helium gas. This could have come from the alpha particles by picking up the 2 electrons. Thus, it must be recorded that alpha particles were the doubly charged helium ions. So how to determine the range? The Bragg has produced evidence that alpha particle has got a different range. So the alpha particle, which is emitting from the source S, which is kept in the lead shield, will travel a distance called D to the ionization chamber consisting of the plates called P and G. And G is the metallic gauge and P is a plate which is parallel to each other, maintains some potential difference called V. So if the upper plate is connected to the electrometer for measuring the ionization potential by the alpha particle within the narrow region between P and G, then the distance between the alpha particle source and the ionization chamber is varied by moving the source. So this is the curve that relates the specific ionization. What do you mean by specific ionization? The number of ions produced by the alpha particle per unit length of the path with the distance from the source. And this curve is called as a Bragg's curve. This curve gives you the specific ionization along the path of the particle, which reaches maximum and then falls rapidly to zero, makes a slight angle in the curve before the zero line is reached. So the specific ionization increases steadily at first and when it moves away from the source. Ultimately, a point of ionization reaches when the electrons attach themselves to the particle. So the tail and the angle of the curve, which is called as a straggle effect, arises from the fact that alpha particles do not lose exactly the same amount of energy in which they encounter with the molecules in their path. So it is also partly due to the formation of helium plus ions by the attachment of one electron to some of the alpha particle. These ions still possess ionizing power and hence cause a slight extension of range before become the neutral atoms. So this method is not well suited for the weak sources, and for the weak sources, Geiger and Nuttall have shown the experimental arrangement as shown in the figure. So here the S be the source of the alpha particles, which is placed on the rod at the center of the glass bulb called A. And this glass bulb is silvered inside, and the high voltage is applied between the bulb and the metallic holder of the source. And the radius of this bulb is greater than the range of the alpha particles. Since the range is directly proportional to absolute temperature and inversely proportional to the pressure, the alpha particle is able to reach its wall. The saturation current for the different gas pressure is measured by giving the ionization curves as given in the diagram. So the ionization current is measured by the electroscope which is constant as the pressure is decreased until after the particle have begun hitting the wall. If then falls off, since the particles are not producing as many ions they are capable of doing, at the sharp turn over the point of the curve, the alpha particle reaches the silvered wall of the bulb, so the bulb radius is range. So the range for the particular gas pressure has been measured. Since the range of the gas is inversely proportional to the measure, the range of the atmospheric pressure can be calculated easily. And these alpha particles are having the high penetrating power, which could even penetrate in the few sheets of paper or the thin aluminum foil, and hence it can travel through the several centimeters or few distances in air, which indicates that range depends on the medium through which it traverses. And Bragg also observed that atomic stopping power varies directly as the square root of the atomic weight. So the range is measured by the different methods with the help of the Wilson cloud chamber of gases, a bubble chamber for liquids, and the photographic emulsion of solids. So the energy of the alpha particle can be determined with the help of the magnetic spectrograph, which is also called as the mass spectrograph. The main part of the instrument is nothing but the electromagnet, which focus the alpha particles of various energies at different points. The alpha particles from the radioactive source merge in a narrow beam through a defining slit as shown in the figure, and this magnetic field acts normal to the plane which bends the alpha particle through an angle of 180 degree. The chamber slits helps to reduce the scattering of alpha particles from the walls of the vacuum chamber. The particles with the same energy have the semicircular paths of same radius, which are detected by the photographic plates or with the counters. The resolving power of magnetic spectrometer is very high, and you can also use the widely used detectors such as ionization chambers, which have got very weak resolving power but can detect minute quantities of alpha active substances. So the Geiger-Nuttall law. The Geiger-Nuttall law relates the speeds of the alpha particles passing through the various thickness of mica of known stopping power. So Geiger law is stated as R is equal to A into V naught cube. What is R? It is a range which is in meters. V naught, initial velocity. So the energy E naught of the alpha particle is related to the velocity, and hence it is found to be 2.08 into 10 power minus 14 V naught squared, from which by rearranging and by finding the relation between the energy and the range, the R value is estimated to be around 0.003 E naught power 3 by 2. What is E naught? It's an initial energy of the alpha particle in million electron volt, and R be the range in meters.